All right, I think it's about time to get started here. I'm Stephen Kinsley. I'm the president of the Ohio Dam Safety Organization, and we're the ones sponsoring this webinar today. The probable maximum precipitation, 20 years updating the HMRs and what to expect through 2100. The presentation will be given by Bill Capel. Mr. Capel is the president and chief meteorologist of Applied Weather Associates. He's been the project manager, technical lead of all aspects of AWA work, ranging from PMP development to climate change analysis to risk quantification since joining AWWA in 2003. Prior to joining AWA, he served as an on-air meteorologist at various television stations across the country. He has been a guest instructor at the University of Colorado in Colorado Springs and a guest lecturer for the Tailing Center and Mine Water Waste Enclosure course. Has published numerous peer-reviewed articles on extreme rainfall and has provided presentations at numerous conferences on various meteorological topics. If you guys have any questions today, please put them in the chat and we will get them answered at the end. Go ahead and take it away, Bill. Thanks.
All right, thanks a lot. And obviously, everybody, thanks for spending your lunch hour with me. I really appreciate that. I kind of laugh at my own title there. If I knew what was going to happen through 2100, I'd be pretty, I'd, be rich or something, right? We can't even get it right through tomorrow, but we can make a guess at least. Anyway, hopefully you guys are excited to kind of learn about where we've been and kind of where we're going in the world of extreme rainfall and probable maximum precipitation development, and of course, what that means for dam safety and infrastructure. So let me get going here. And again, I do hope we have some time at the end for questions as well, because it would be great to be able to hear some feedback or get into some other discussions if we have some thoughts going forward. So real quick, when we talk about probable maximum precipitation, I just want to make sure everybody's clear that that of course represents the theoretical upper limit of the most amount of rainfall that could ever occur for a given location for a given time of the year over a given area size. Why that is important? Well, because when you think about critical infrastructure like dams, hydropower dams, flood control dams, water control dams, etc., they need to be built in a way where they do not fail or cause any loss of life or loss of significant infrastructure if they're rated as a high hazard dam. And to make sure that that happens, those facilities have to be engineered and designed to handle the probable maximum flood, which is awesome. But where do you understand what the probable maximum flood is? Well, you get that from understanding what the probable maximum precipitation is, or the PMP. And that's our job, is to define that, understand that, and refine that as much as possible. But like most good things in science, we weren't the first ones to come up with this concept or start it. The process started way back in the 1940s with the Weather Service and the Corps of Engineers putting together information to try to kind of consolidate information that was out there and kind of understand the dam safety community and what they could do to support those processes. The very first study actually was done up in Vermont in 1940, and then we've built on from there with the National Weather Service, the Corps of Engineers, Bureau of Reclamation through the 40s, 50s, 60s, 70s, and then in the 1990s they stopped. And of course, storms didn't stop happening, and dam safety continued to advance, and needs for upgrades and spillway rehab continued. So somebody had to step in and take over those processes and continue the science and build the science. And that's where Applied Weather Associates came in, and starting in the 1990s, and we've continued since then. So that's kind of the brief timeline and background of probable maximum precipitation and kind of where we've gotten to today, which we'll talk about more in a second. Now, for Ohio specifically, there's some really cool things happening around the area that I want to show you. So first of all, the nice thing about what we've been doing over the last 20 years is really filling in these gaps and updating the old and outdated technology. Now, you have to understand probable maximum precipitation, the foundation of that is storm analyses and analyzing the most extreme events that could ever happen. So me as a meteorologist, it's the best thing in the world. I get to analyze the biggest storms that ever happened. I get to develop information and data and provide it to engineers and hydrologists to solve a problem and to check safety of dams, and a lot of times save a lot of money for the communities. So I get to see the whole picture from concept to analysis to design and implementation. And as you can see, we've done a lot of work over the last 20 years, Ohio right here specifically, but even in and around Ohio, a lot of information that's been used to update the PMP and understand the storm dynamics and storm information within the state. We've been able to do a lot of follow-on studies for water districts, sewage control, those kind of things that understand what rainfall looks like, not just at the level of PMP, but also at other levels that are critical for water design, to the 100-year storm, 1,000-year storm, and so on. So a lot of information there that we've been able to utilize from around the region that's specifically relevant for Ohio. And we continue to update all these areas, not only around the US, but also in much of the world, because this is an ongoing process, right? Again, these scientific advances and the storms continue to happen. We want to make sure that we have the best information and data implemented at all times to make sure that dams are safe and the communities are safe and the infrastructure is safe. So a little history. So first of all, way back in 1993, it's amazing to think that's already 30 years ago. But way back in 1993, the first two studies were completed for the states of Michigan and Wisconsin that were completed outside of the purview of the National Weather Service. The founder of AWA at that time, Dr. Ed Tomlinson, led those two studies and received approval from FERC, the Federal Energy Regulatory Commission, and the review board that was part of that study, which included the authors of the National Weather Service's hydrometeorological reports, HMRs. So that was kind of the first process that was begun from a statewide perspective. Then we skip ahead all the way to 2008 when the next statewide study got done, and that was in Nebraska. And then very quickly after that, Ohio in 2012, 13, and Arizona got done. And then we've continued on from there. And most recently, we've completed the state of Hawaii. Actually, I got to update this. We just completed the state of Hawaii this month, actually, and are just starting the state of North Carolina. So I think we're up to about 22 states now that have been updated through time. But what's amazing is, if you're in these things long enough, things begin to get old. I mean, already Michigan and Wisconsin being 30 years old, it's always good to continue to look at the storms, see how that science has been changing over time, and if any updates are needed. The other part of that process, of course, is by updating these studies and the data sets, you're continually capturing any changes in climate that may be occurring and any of the differences in storms. And we'll talk about that in a second, what that means. But that's all part of the process, is to continually update these and keep them updated with the most current information. Now, as you look ahead to what this looks like, and I want to make kind of a fun little map here that shows when you put all these pieces together, how useful this information is. So just as a quick example, this is a general storm, PMP depths from several of the studies that we've completed, and you put them all into one map. You're kind of looking from a visual perspective. Do these make sense? Do they fit? And do the values all kind of fit in together? And the reason I show that is because if you looked at this from an HMR perspective, it would not look like this. It would be very different. You get these in the HMRs, these kind of simplified contours that don't really reflect reality at all. And that's part of the process of updating these and getting it. The whole point is to get it more accurate, to reduce uncertainty and reduce risk for the various infrastructure. That's the whole point of doing all these. So as we talk about the progress and get into what's coming next, the point of that is to continually update the storm database, right? As new storms happen, we want to make sure we include them in these data sets. And we always are testing our previous PMP depths to make sure that they're safe, that they're reflective of the current data sets, and they're appropriately enveloping whatever happens. Also, there's a lot of things that have been improved over time on the scientific side, and there's a lot more to be done. So when you think about probable maximum precipitation, it's very important to think about it in terms of storm type. So think about Ohio, for example. Back in March of 1913, you had a huge flood event in Ohio that was a result of a March rainfall event on top of melting snow and frozen ground. Well, that's a lot different than a storm event you might get in July or August, where you might have a line of thunderstorms coming through, like Worcester, Ohio in July of 1969. Or College Hill, Ohio, where you have short duration, high intensity thunderstorms that produce a lot of rainfall over a short duration that are driven by convection. In some cases, you might even get a remnant tropical system producing moisture in Ohio. I'm sure, hopefully none of us on this call are old enough to remember, but back in 1878 in Jefferson, Ohio, there was a very large rainfall that occurred from a remnant tropical system that moved through the region and caused a lot of problems. So you have all these different storm types that can happen in a given region and cause different flood type events. Some of them are large events over large regions and a large volume of rainfall. Some of them are short duration and high intensity events with a thunderstorm producing, say, 6, 7, 8, 9, 10 inches of rain in just a couple of hours. So we always want to be looking at PMP in those types and trying to make sure we understand how those would affect different structures and different runoff scenarios and so on. Now, the other part of that is to make sure we understand the different aspects that go into those storms, because there's a lot of really cool information that can come out of those that can be used for a lot more than just PMP development. As I mentioned, those storm databases provide information for stormwater management, sewage control, highway design, other types of infrastructure that don't need full PMP, but that can really benefit from understanding what rainfall looks like at a much more localized scale and more often recurrence interval. So there's other cool things there. The other part that's so important, you know, when you're talking about engineering and application of these rainfall amounts, how do they fall in time makes a very big difference, right? There's a lot of standard products out there from the National Weather Service, from the National Resource Conservation Service, NRCS, Corps of Engineers, and so on, that provide idealized temporal patterns of accumulation. But when we have this database of storm information to draw from, we can really drill down on each of those storm types and how those patterns actually accumulate in Ohio or in other areas specifically. And that can make a big difference when it comes to designing infrastructure. And then the other part of that is all the things I've talked about up here are all deterministically derived values that provide information. But the other important aspect is to understand the probability associated with those values. So we've, in most of our studies in the last 5-10 years, always provided a probabilistic estimate as well, which assigns a recurrence interval to these values. Now, obviously, when you're out at the level of PMP, your recurrence intervals are pretty darn rare. And of course, your confidence intervals are very wide as well. But it does help provide and set the stage for what it could be and how rare those events are. And then that can be used in conjunction with other assessments on the probabilistic side. All right. So again, I talked about how important it is to analyze storms and keep that database updated. Well, I just want to show you an interesting thing here. This is from HMR 51, the hydrometeorological report that was relevant for Ohio before we did our study. And what you'll see here is HMR 51 basically covered the U.S. from about the eastern plains of Montana, Wyoming, Colorado, New Mexico, all the way to the East Coast, and from Canada to the Gulf of Mexico. In that entire region, they only had about 100 or so storms to deal with to try to define PMP. And you'll notice, very interestingly here, no storms at all, or hardly any storms at all, in Illinois, Indiana, Ohio, West Virginia, Kentucky, Tennessee, and so on. So they had a lack of storm data in this region specifically for Ohio to derive PMP estimates. Now, on one hand, that's okay because you're able to bring in storms from these other regions and move them into Ohio to use for analysis, but it would be good to fill this gap in with storm data in the region that's specifically relevant for the area to test it and see if it's okay. So this is one of the limitations, of course, that we come in and correct, is filling in these gaps with storm information and continuing to update that database. And so what does that look like? Well, when you take a look at the storm analysis we've completed over the last 20 years, you'll notice in Ohio specifically, we've analyzed several storm events right in the state and right around the state. So if you can go back to that picture, this gap here is filled in very nicely by the storm database that we've been working on over the last 20 years. So that gives us more confidence in the outputs that we're deriving and the PMP estimates. And it allows us to really compare and test what we're doing today versus what was done in the past. That's an important aspect of it. Now, for Ohio specifically, you know, hopefully some of you have seen the outputs and are used the outputs over the last 10 years or so. And these are just examples of how the PMP was done for Ohio in the past. So here on the left is the 6-hour 1 square mile PMP depths. And you'll notice we basically plotted a series of grid points across the region, covering the entire state and then providing a buffer. And then at each of those grid points, we calculated the PMP depths at that area size and duration. And they just did a simple plotting of what those look like. Now, an important aspect of that is if you're familiar with HMR 51, for example, it does not provide PMP down to 1 square mile. It's stopped at 10 square miles. And of course, there's a lot of basins in Ohio and surrounding regions where 1 square mile or around that area size, certainly less than 10 square miles, is actually the size of a given basin. So it was critical to be able to have that information at those area sizes. So the PMF evaluations and the engineering evaluations could be done at the specific area size relevant to the basin. And at the right side here is a 24-hour 10 square miles. So same thing, values derived at each of the grids plotted and then simply drawn across the area. Now, since Ohio was completed over the last 10 years, we've advanced this technology quite a bit and utilized the power of GIS and the power of big data computations to really continue to refine and improve this process. So you'll notice the grid spacing here that was used in Ohio. As we went on to further statewide studies, that grid spacing went down significantly to basically 2.5 square kilometers or 2.5 square miles. And so we now have the ability to process these calculations on a grid by grid basis that's much, much more refined and specific to each state. So for example, here's a look at Pennsylvania. And this map is plotted by using all the thousands and thousands of grid points that we were able to calculate PMP across the state in the same way we did Ohio, but a much finer resolution. Now, one of the reasons we do it that way now is because it's very important in areas where topography has an effect on rainfall that we're able to quantify those aspects in time and space in high detail. So if you think about the Appalachians in Pennsylvania and Virginia, for example, it's very important to be able to quantify those spatial variations that occur. I mean, you look at Virginia, the PMP depths have a huge amount of spatial variability over a very short distance as they interact with the Blue Ridge Mountains and so on. When you come out to New Jersey, where you just have coastal and then Piedmont and then finally up to the Appalachians, that variance is much less. Similar to Ohio, that variance is much less. It looks like a lot here, but if you actually look at the magnitudes, you're only going from 17.5 inches to 20 inches across the entire region. While in, like I said, Virginia, you'd be going from, say, 10 inches up to 30 inches over a very small area because of the topography. Similarly, as you get into other parts of the country where we've done this work, the variations across Oklahoma all the way down to Louisiana, Mississippi are relatively small. But when you get into, say, Tennessee and back up into western North Dakota or North Carolina, you start to get some pretty big differences again. And then, of course, in the Rocky Mountain regions, those dramatic differences can happen very quickly. So it was important that we had a process to be able to analyze the PMP depths at that very fine grid scale and understand those variations in time and space and area size that occur because of the topography. Recently, as I said, we continue to move on these studies as we went up to North Dakota. This was a fun one we just completed because North Dakota, as you can imagine, has two types of PMF scenarios. One, of course, is the summer times, fall times PMP, PMF, just like Ohio. But of course, they also have a very large flood events that happen quite often because of spring snow melt with rainfall on top of that. So we had to derive both a warm season PMP and a cool season PMP. And with the cool season PMP also provide 100-year snow water equivalent depths, snow melt calculation ratios, and so on, so they could model which one would be a worst case scenario. You can imagine there's cases on the Red River of the North where the summer PMP is competing with the spring PMP, PMF, and you kind of have to decide which one is worse and be able to model both scenarios. Moving to the tropics, this was a fun part, of course, too, especially, obviously seeing the devastation in Maui and what's just happened there is unbelievably heartbreaking. And, when you think about what caused that, of course, is very dry weather and very strong winds, a meteorological component to that. On the other side of the equation, as you look at the rainfall that can happen, and this is also pretty concerning, I'm sure you understand this in Ohio too, after you have a fire, the runoff characteristics of a given basin can change very quickly, right? So you burn the ground, the rainfall runs off much more quickly and can cause a lot of problems with debris flows and so on. And so now one of our concerns in Hawaii, which we just finished, is as we get into the rainy season, which really starts in November and goes through the spring, these burned out areas of Maui and the Big Island where they just have these issues, we really do now have to worry about, man, if they get one of these types of rainfall events that are even close to a major event that could cause a problem, there's going to be some serious debris flows and mud flow problems and runoff characteristics. So it's one of those things where you see how all the interplays of meteorology and weather and climate come into play, both warm and cold, or I'm sorry, hot and cold, warm and dry and wet, and everything else. Kind of all. There's always something going on, right? It's never static. It's never quite in balance, and there's always potential problems. So we really want to have, hopefully they have time to clean up and stabilize those areas before the wet season starts out there, because that's just going to cause some more problems. But as you can imagine, both Puerto Rico and Hawaii can get a lot of rainfall. In Hawaii, over a 24-hour period, these values are up at 60, 70 inches on the wet sides of the Big Island of Hawaii and Maui, Oahu, and Kauai. And it's a lot of rain. Obviously, if you've been out there, you know that. But the amazing thing about places like Hawaii is you can go from 70 inches of rain on one side to 10 inches as soon as you get over on the other side. It goes wet to dry very quickly over there. And of course, that's one of the things that exacerbated the problems in Maui. But all those fires were on the dry side when you had downsloping winds coming off of the higher elevations to the east. And then you had the problems that occurred, of course. So as we go forward on the statewide side, we kind of talk about what's next, right? We've done all this work. We have all these data sets. How do we use them? How do we get the information out to people to utilize? And how do we continue to reduce uncertainty and ensure things are safe going forward? Well, there's a lot of data out there that we try to disseminate and provide and share as much as possible. Part of that process is to have a nice web interfaces that make it easy for anybody to access the data and to utilize the data. Not everybody's an expert in GIS. Not everybody has a desktop GIS they can use. So one of the next steps we're doing is to put all of our statewide studies I just showed into one consistent database across the US and make that as a web interface, so you don't actually have to have GIS on your own to be able to get the outputs and run things. This is the example from Colorado, New Mexico. It's a simple web interface where you just go to the website and you can enter in your basin or area of concern or your dam location, and it will produce the same outputs as you would have from the actual study if you had GIS. This is one thing we want to talk to Ohio about, to be able to put in place for them as well and make it easy for everybody and anybody to be able to use the outputs. But that's an ongoing process that we're working through. Okay, so then the next question is, what's next, right? What's next? Well, PMP, because it's a storm-based data set, always continues to be updated. But then we have to ask ourselves, what about climate change? Well, what about climate change? So you have to understand that climate is changing. It always will change. It always has changed, whether we're here or not. The Earth is constantly trying to get into balance. And of course, that will never happen as long as we have a tilt in the Earth's axis and we have an orbit around the sun that is not perfectly circular. So climate's always going to change. Now, the question is, what would those changes be going forward, and how can we respond to them, and how can we prepare for them and make sure that our infrastructure is appropriately designed and resilient? So we have things like climate change models that try to replicate what could happen in the future if things were to go the way we think they are. Now, every aspect that we're going to talk about with climate change models is uncertain and unknown. Just like every model, all models are wrong. Some are better than others, but they all produce outputs that are interesting and can be useful and that we can play what-if scenarios with. So what I'm showing here are the global climate change models, which cover the entire globe, obviously, as noted in their name, but their grid spacing is very coarse. As you can see, just 1 or 2 grids covers the entire state of Ohio. So we need more detailed information from that to be usable in these analyses. And so we have to take this output from these global climate models and downscale them to a local level with regional climate models. And this is done by a number of academic and government groups around the world. They do these downscaling processes and then make the outputs available for users to be able to analyze on a local scale. The current process uses what's called CMIP 6, the 6th version of these downscaled climate models. And it provides the information that we need at AWA to be able to compare this to the PMP data that we've done. So on those aspects, lots of people do climate change assessments. But nobody does climate change assessments with a specific background in relationship to probable maximum precipitation that we do, because we have both sides of the equation. We've done the PMP work, we have the context and data from which to use and compare that to the climate change assessments out there, and have the context of what's the uncertainty in those PMP values, right? So the PMP for Ohio, for example, very straightforward to analyze, but in each of those processes, there's a huge amount of subjectivity and judgment. And when you put the uncertainty of each of the steps of PMP into the final product, you have a value, but that value has a range of outcomes that could easily be plus or minus 20%. So we have that context and understanding. We know how the sausage is made. Now, having that and understanding how the climate change projections work, we can put the two pieces together and really have a true outcome of, hey, are the climate change projections projecting something in the future that's beyond the range of uncertainty already built into our PMP estimates or not? And so we can look at it in those ways. Now, as we go through this process real quick, I'm going to tell you how that's done. Climate change projections, I'm sure you've probably heard a lot about these. They have different future emissions scenarios that they try to model against. And this is just a graphical representation of that. The yellow line here is the middle of the road scenario, 4.5. That's the one we're following. That's the most likely outcome. And then we also look at the most extreme outcome, 8.5, just to bracket what could happen. But when it comes to application, 8.5 is not recommended to be used because it's almost no chance of that happening. That would basically be us turning on every coal-powered power plant and building a new power plant every day across the country. That's not going to happen. It might be good for energy prices. Maybe we should be doing that, but that's a whole nother story. But we do those ones just because we want to bracket the most likely outcomes as we go through these process, and because these scenarios also have the meteorological outputs that we need to compare. As I mentioned, we're always talking about uncertainty in these analyses. Anybody that tells you they know for sure what's going to happen, you know for sure that they're wrong, right? I don't pretend to know all the answers or know this perfectly. We're dealing with Mother Nature. We're dealing with meteorology. We're dealing with climate. We have a lot of uncertainty and a lot of unknown. And many of these aspects we just don't understand yet. We don't fully have characterized or analyzed. And I hope we never do, because the fun part of being a meteorologist is how many times you're proven wrong. You never know all the answers, right? You're always trying to discover what's going to happen and hoping you can figure out the next steps, but you're never quite there. So that's kind of the fun part of it. Anyway, when we get into the climate change stuff, we use the plus or minus 20% that I mentioned to be considered within the natural variability, within the uncertainty range we already have. So if we see climate change projections that are beyond that plus or minus 20%, then we think that might be something useful to plan for. If they're within that range, when it comes to PMP and extreme rainfall, then we feel like we've already got that enveloped in the current processes. So what does that look like when we kind of put these together? Well, these are climate change study locations that we've completed over the last 5 years or so around the world. You can see the US here, Europe, South America, Asia, and Canada. And what we've done is we said, hey, from all of those studies, what are we seeing as outcomes from a temperature perspective through 2100 and a precipitation perspective over different timeframes through 2100? Well, not surprisingly, partly because the models are tuned this way, but also maybe because what's happening, it could be both. From a temperature perspective, every climate model is showing a rise in temperature through time. Okay, so that's consistent. Now, what way we have it plotted here, the larger the circles are, the larger the range of temperature increase. And so you'll notice, for example, we just completed an assessment for a basin just outside of Chicago. And that one was producing about a 3-degree, these are in Celsius, but a 3-degree increase in temperature by the year 2100. So when we do these, we go from today through 2100. So if it's 3 degrees by 2100, it's a simple rate of scale change through time. So you can pick any year within that duration and get what the temperature change would be by that year. So 2030, 2040, 2050, whatever. And again, these are in Celsius, which is important because the way that the atmosphere works, the warmer the atmosphere it is, the more moisture it can hold. And there's a simplified equation out there called the Clausius-Caperian equation, which says every 1 degree Celsius warmer the atmosphere is, it can hold 7% more moisture. Now, a lot of people just stop right there and say, oh my gosh, we're going to be 3 degrees warmer by 2100. That means we're going to have 21% more moisture in the atmosphere. That means our rainfall is going to be 21% higher. Fortunately, Mother Nature doesn't work that way. It's never that simple. It's not a linear one-to-one fit from going warmer to more rainfall on the ground. There's a very chaotic, non-linear set of processes that take moisture in the air and convert it to rainfall on the ground. Some of them are positive, some of them are negative. And the way that the climate works, as you get warmer, some of those feedbacks actually reduce the ability of the atmosphere to convert moisture in the air to rainfall on the ground, and some of them increase it. So it's kind of battling back and forth. The reason I'm saying all that is because when you look at the precipitation projections, they do not follow the temperature projections that we're showing here. It's very much dependent on the seasonality, the storm types of a given location, what types of storm causes the most extreme rainfall, and how those things interact from a different type and different time of the year. So temperature-wise, everybody's consistent, showing an increase, some more than others, but precipitation-wise, you'll notice here, if we go to the 1 day, we do not see that same aspect. So here, we're looking at the 1 day precipitation frequency change. These are directly from the climate change projections. The red circles are showing less than a 20% increase by 2100, and the green circles are showing more than a 20% increase. So again, focusing on that study just outside of Chicago, you'll notice it said about a 3-degree increase in temperature. That would equate to a more than 20% change of precipitation. Yet, on the precipitation side, it is not showing that. So again, that's just pointing out that you really have to drill down into these at a site-specific level and look at these parameters individually and see what's happening from the projections, because it's not straightforward as to what could be happening. In fact, most of the areas in the US don't show a significant change in precipitation until you get to the desert Southwest. But again, when you drill down to these by season, these increases in New Mexico and Arizona actually occur in the winter time, not during the time when they get most of the rain in the North American monsoon season. As you go to a 3-day, again, most of the US is showing less than a 20% change by the year 2100. So that's important, again, because we're talking about the most extreme rainfalls. I'm not talking about the 5-year event, 10-year event, 50-year event. I'm talking about 100-year recurrence intervals and beyond. And we're showing that, or the climate change projections are showing, those are still within the range that we've already observed in the past, that plus or minus 20% difference. And then finally, from an annual perspective, again, all of these in the US are showing less than a 20% change through time, again, which is important because that gives us some confidence in the way that our infrastructure has been designed, and hopefully we're at a point where we're safely designed and properly evaluated going forward. Now, let's take a look at how that's done real quick, because I want to give you a sense of what it looks like when we do climate change projections. So we just completed this for the state of New Jersey as part of the PMP update for that study. And you can see basically New Jersey here, the areas and the basins that were specifically analyzed from a climate change perspective. We chose basins in different regions and different area sizes to see what was going on when you apply the projections to those various areas. As I mentioned, these are the temperature, which is the middle plot, dew point, atmospheric moisture, the bottom plot, and then daily rainfall on the top. So temperature and atmospheric moisture show a nice rise. The blue area is the model projection, just going forward through 2100, the blue and green lines. And you can see on temperature and moisture, those have a nice increase through time, pretty steady between all the models. But when you look at the rainfall, the daily rainfall, again, the reddish orange area is the historic period, and then the blue and greens are the period going through 2100. We don't see any trend, any significant trend. There's just up and down days, just like there's been in the past, but there's no upward trend. So the point being, the temperature increase and the moisture increase are significant, but the rainfall on the ground is not a one-to-one response. It's a very chaotic, nonlinear system, and that's reflected in the models. And so when we do these analyses, we look at this in a couple of different ways. We look at a trend analysis to see what's been observed in the past and if that's changing going forward at a significant level. We do these on monthly, annual, seasonal analyses. So we can look at, hey, is the month of January looking different than the month of June and the month of September? Are there differences inside of the data sets that need to be considered beyond just a daily or annual aspect? And we look at it from a frequency analysis. And we also look at it, again, from seasonality perspective. So we can capture all the components. Just as an example from the New Jersey study, for example, from the historic trend analysis, the data that we actually were plotting basically showed no trend, yet temperatures showed an increase. Again, that's talking about what I said before. Then as we went forward and we looked at the 4.5 and 8.5 scenarios going into the future, those begin to show a pretty significant trend, especially as you got to the 8.5 scenario. So when we look at the historic period with no trend in the model and 8.5 showing a pretty significant trend between them, that tells us that something's happening there as we go into the future and we continue to add temperature increases and so on. And it gives us a sense of which models are performing the best, which ones we might want to rely on the most, and so on. From a frequency perspective, again, keep in mind, we're looking for that plus or minus 20% change. So for this example from New Jersey, from a one-day perspective, there really was no change. And in fact, you could argue there's a little bit of a decrease in the 4.5 scenario for this particular location, in the summer especially. And so why do we break it down by summer and winter? Because if your flood control operations, your river management operations, your water storage operations, whatever it might be, if you think about your operating rules, if you're going to be getting drier in the summer, that could be pretty important, right? Conversely, this was showing an increase in the wintertime. So maybe that's just as important to know for flood storage, for flood runoff management, and so on in this particular case. So we try to break it down by duration and season so we can really see what's going on within all the processes. We also look at all the models that are available in standard whiskey plots and probability plots so we can see what's going on. You'll notice in these ones for temperature, pretty consistent. That's a pretty tight fit around the mean between the 25th and 75th percentile, with a couple of outliers up there that you could probably say, why are those so outliers? And maybe we should disregard those. And therefore, how much confidence do we have in the mean values? Temperature is pretty tight between all the models. But as you go to precipitation, of course, we get a little bit more of a range. So here's your precipitation, and you can see that range in some of the outliers of the models and variation.
Things to do.
Okay. So again, same thing here, just looking at the models all kind of put together. We're looking for consistency between the climate change projections. That gives us more confidence in what's probably going to happen. Again, though, the main thing here is these values of 9 and 10% are well within our natural variability and what we've observed in the past. So in this example for New Jersey, we feel good that the values we just derived from the PMP estimates for dam safety are adequately capturing that range of variability that's going to be going on in the next 50 to 75 years. And then the final outputs are put into a nice table for the engineering community to utilize. So for the 4.5 scenario, which is what we recommend, and then the median, which is what we recommend from all the models, there's basically very little change in precipitation in this particular example. It's well within the range of natural variability, plus or minus 10% for all intents and purposes. And so why do we say that? Because then we can say, hey, going forward, we really feel confident in the values we just derived are going to be plenty adequate for our design standards and so on going forward. We don't see any significant change in 1 day and 3 day precipitation for extreme rainfall and PMP. And the things we do see are a little bit changing of seasonality. So you might want to think about what that might be for water storage and water management and flood and so on. But we don't see any issues in this particular example of having to resize spillways or update dams because of future climate change. It looks like it's already captured in the process that we just implied. So that's the important outcomes of these. You know, as we've gone through this talk today, we've talked about kind of where we've been, the start of the probable maximum precipitation process, where we've been going over the last 20 years, the updates we've made, the cool different ways to analyze PMP on a very refined, gridded level, and updating these databases. And then we said, okay, well, what's going to happen next? Well, we're continually looking at these climate change projections as they come out to see and ensure that the PMP estimates and extreme rainfall analysis we're completing are adequate and continue to provide the safety that we require and capture the uncertainty in the process. And the good news is, as I just showed, for the most part, in most locations around the country, the climate change projections of changes in precipitation are captured in the processes that we currently have. Now, as I said earlier, there's always a lot of unknown and subjectivity in that. It's very important that we continue to advance the science, continue to study these outcomes, and any changes going forward. I mean, every few years, new climate change projections come out, and we should continue to look at those and apply those and see if anything's changing. As new storms happen, it's very important that we continue to look at those storms and see how they compare to the ones that we've already used, and continue to update that storm database and continue to draw from that immense amount of information from those storm analyses to use for so many other aspects in the water management, water conveyance, flood storage, infrastructure design aspects. There's so much great information out there, and that most important that we always continue to be humble, and that we always understand we don't know as much as we think we do. And Mother Nature's always throwing us surprises and kind of making us understand that we're not quite as smart as we think we are, and that we continue to work together, right? I mean, it's important that I'm not off doing this by myself outside of the hydrology and engineering communities. It's a team effort. We need to understand the needs of what's out there and the infrastructure and so on, and make sure we're analyzing information and providing products that help and answer the questions that are needed. So hopefully you guys enjoyed that presentation. Obviously I love talking about this stuff, and I'm happy to answer any questions and anything you might think of offline, and always happy to share thoughts on the meteorological and climatological conditions around the area. So with that, I'm going to wrap up my presentation and open up for any questions or thoughts or feedback. So I will stop and see if there's any questions out there.
So just a reminder, if you have questions, if you want to go ahead and put those in the chat.
And it doesn't have to be about what I just presented. Feel free to ask me any question about weather or climate or anything else too. I'm happy to talk about all that kind of stuff. So. All right, well, hopefully that means everybody is eating their food and enjoying their lunch.
Or else
And by the way,
or else you've given us so much to think about. Where
I threw something that I could probably spend 5 hours talking about in 45 minutes. So there's a lot to go through. The bottom line of all of that presentation is that the PMP estimates that we're deriving here, we should feel good about the safety that they are applying for Ohio. I mean, the fact that in the last 10 years, all the new studies we've done around Ohio and the storms we've analyzed haven't changed the PMP estimates is important, right? We've had storms that challenge those estimates, but they haven't exceeded, and that's a good thing. And the other part I didn't mention is when you look at the Ohio study or Pennsylvania or any of the other studies, it's always a mix of old storms along with newer storms that control the PMP depths. And that's what we want to see. Like if we did these studies and the storms that were controlling the PMP depths were all occurring in the last 10, 15 years, then we'd want to say, oh man, we're seeing something obviously changing. But we're not seeing that. For Ohio and surrounding regions, like I said, the storm in 1878 in Jefferson, Ohio, still controls PMP depths in a lot of cases, along with newer storms like Big Rapids, Michigan in 1986, or Hurricane Agnes in June of 1972, and so you have a mix of old and new in the data set that are controlling of the PMP depths, and that's exactly what we want to see, because that means the processes that we're doing are incorporating all those things. Hey, so it looks like we're getting a couple of questions. I think people put down their forks for a minute and started typing. I like it. So let's see what we've got here. So Greg says, does the analysis incorporate an increasing rate of change or assume a constant trend? Yeah. So that kind of refers to what we talked about a lot, non-stationarity in the climate. As I mentioned in the very beginning, you got to understand, so when we do these analyses, we're looking at the entire period of record from the mid-1800s through today. Now, during that time frame, climate is not stable. It's never stable. It's always changing. So any changes in climate that were occurring in the past or we're capturing in analysis. Now, going forward, when we do these climate change assessments, we do exactly what we said. We incorporate a rate of change through time. So if we have a value today of X and a value by 2100 of Y, that line to get from X to Y is the rate of change through time, and that allows you to evaluate a condition at any time in the future using that rate of change through time. All right, so another question from Nicholas. He says, is there any relation between results you've shown to the lesser frequency storms? Good question. So a lot of times, the more frequent events, say again, the 2-year, 5-year, 10-year type events, do show a significant change or trend of increase through time. It's the storms that we focus on, the most extreme storms, that really aren't showing much of a trend. Now, why is that happening? I don't know. That's the fun part about this. But most likely, it's because when you have precipitation, it's a very simple process. It's a function of two things: moisture available in the atmosphere and lift in the atmosphere to get that moisture to condense, turn into clouds and precipitation. So when you think about extreme rainfall events, those occur when you have high amounts of atmospheric instability, high amounts of moisture in combination. Now, to get atmospheric instability, just like anything else in the engineering world or the physical world and so on, the larger the contrast in temperature and pressure in the atmosphere, the more instability you have. So if it's colder to the north and warmer to the south, you're going to have a larger contrast in temperature, more instability, more rising motions, and more potential for heavy rainfall. Well, if you take climate models at their word, which you shouldn't, but if you take them at their word, the poles are warming up faster than the equator. So in general terms, what is that doing? Well, that's lessening the temperature gradient across the globe. If the temperature gradient is lessening, you're going to have less of a temperature gradient, less of a thermal gradient across a given area, and potentially less instability, therefore weaker storms. Now, on the other hand, if you have more moisture and you still have enough instability to create rainfall, maybe you have more frequent light rainfalls and less frequent extreme rainfall events. That could be part of the process. Who knows? That's certainly in the mix, and that could be one reason we're seeing more overall rainfall, more lighter rainfall events, and less extreme events. Maybe that's a possibility, something we think about all the time. We're trying to test. Also, let's talk real quick. A question here. It says, can you talk briefly about the processes you use to help states develop annual exceedance probabilities of data? Absolutely. Annual exceedance probabilities. So if you guys are familiar with NOAA Atlas 14 and then what's coming next, NOAA Atlas 15, those probability estimates provide 2 years to 1,000-year recurrence intervals of rainfall at different durations. The problem is there's a lot of things that need to be known beyond the 1,000-year recurrence interval. So when we do our annual exceedance probability estimates, we've already defined that upper limit of PMP from a deterministic side. So we have that upper bounding condition. We also have this immense database of storm information of extreme rainfall and observational data that we can utilize to derive annual exceedance probabilities out to PMP. In this case, often 10 to the minus 6, 10 to the minus 7, 8, 9, and 10. Now, you follow the same process as applied in NOAA Atlas 14 and many other types of studies like that, which is a regional L moments approach following the Hoskins and Wallace methodologies. And you also apply a stochastic storm transposition approach. And when you have those data sets of the PMP depths, the storms that you use to derive PMP and the data sets from those, you have the information you need to derive the annual exceedance probabilities out to those very rare levels. Obviously, when you get out to those very rare levels, your confidence bounds, your confidence intervals are very wide. But having the PMP from a deterministic side to plot against those probability curves and where they cross, you can see the recurrence interval. It kind of helps set the stage from two different aspects and figure out, is our PMP appropriately rare? Is it kind of fitting where we'd expect it to be, say 10 to the minus 6 or 10 to the minus 7? And generally that's the case. And then once you have that, now you have a probability curve all the way from 2 years out to say 10 to the minus 10. And now you know what your 10,000-year storm is, or your 5,000-year storm, and so on. And you can use that information for so many other things, risk analysis decisions, risk-informed decision-making, and so on. And we have lots of write-ups on that. If you want to follow up after, I can give you a lot of specific papers that show exactly how the process is done and the results. So hopefully that was helpful and answered the questions. Again, I want to say I love talking about this stuff. So please, if you think of other questions going forward, reach out to me, ask questions. I'm always happy to share data. Science doesn't work if we're not sharing our data information and we're not trying to solve problems and helping each other out. So thanks again for listening. I really appreciate it. And Craig, Steven, Stara, thanks for inviting me. And obviously, I hope to do a lot more work in Ohio and with Ohio and continuing to keep things safe and going from there. So appreciate everybody's time.
Very good. Thanks, Bill. Can folks email you if they have
Yeah.
further questions?
Absolutely. Let me reshare my screen because my email is on there. And I think it's a lot to write down, and also a phone number. So hopefully everybody sees my screen. Email me anytime. Call me anytime. I work from home, so besides my dog having to listen to this all the time, I'm happy to talk about these subjects and get into some fun details. So don't be shy. It's always good to be able to share knowledge and information, and let's talk about these things. Yep.
All right, very good. We have recorded this, so it will be available at a later date. Do you have anything else, Stephen, you want to add?
No, just one last thanks to Bill.
Thank you, Bill, and thanks for everyone for attending.
Yeah, absolutely. And guys, it's going to be getting hot the next couple of days, next week. So hopefully you're all prepared for that, and enjoy the rest of your summer, and we'll talk soon. Thanks, everyone.
All right, take care.
Bye-bye.